So, here's a wild thought. What if you tried to make an AI smarter by giving it a bigger brain, but it actually made it dumber? It sounds completely backward, right? Impossible even. But for a long time, this was a very real, very frustrating paradox that had some of the best minds in AI totally stumped. Today, we're going to unpack the beautifully simple idea that cracked this mystery wide open and honestly changed the game forever. And I'm not just being hypothetical here. This was actually happening. Researchers were doing what seemed logical. To get a smarter AI, you give it a bigger digital brain. You add more layers for it to think with. But instead of getting these super smart AIs, the results are going the wrong way. The AIs were getting worse. It was this bizarre, counterintuitive problem right at the heart of deep learning. You see, for years, the golden rule in AI was pretty simple. You want a more powerful AI? You make its neural network deeper. More layers means it can learn more complicated stuff, right? It's the difference between an AI that can only see basic lines and one that can recognize faces, objects, whole scenes. The logic was solid. Deeper equals smarter. End of story. Or so we thought. But then, a team over at Microsoft Research was pushing the limits, trying to build these super deep networks, and they just hit a wall. They stumbled onto something that made absolutely no sense, something that flew in the face of that golden rule. They gave it a name: the degradation problem. So picture this. They keep stacking on more and more layers, expecting the AI's performance to just keep climbing. But it didn't. Instead, the accuracy would climb for a bit, then it would level off, and then it would actually start to drop. The AIs were literally getting worse at their jobs, even on the exact same data they were training on. It was just baffling. And this chart really just says it all. You're looking at the error rates. Now, you would think the bigger, deeper 56-layer network would crush the 20-layer one. It should have a lower error rate. But look, it's the opposite. The error is significantly higher. The supposedly more powerful network was making more mistakes. Now, usually when an AI performs poorly, you might think of something called overfitting, where it kind of just memorizes the training data. But this was different. This was a huge red flag because the model was failing on the very data it was supposed to be learning from. That was the degradation problem, and it was a massive roadblock. I mean, how are you supposed to build the next generation of AI if making them bigger just breaks them? And the researchers who found this, Kaiming and his team, they pointed out the logical flaw perfectly. A deeper model should, at the absolute worst, perform just as well as a shallower one. And why is that? Well, because in theory, you could just take that shallower network, stack a few new layers on top, and just tell those new layers to do nothing, just pass the information through untouched. So it should never, ever be worse. But it was. So this paradox was a real head-scratcher. But the solution wasn't some ridiculously complicated new math. No, it was an elegant, almost shockingly simple idea. It was a shortcut. Okay, here's the brilliant insight. Imagine you're an artist. You've got a pretty good sketch, but it's not perfect. Now, what's easier? Redrawing the entire thing from scratch, trying to make it perfect, or just taking your pretty good sketch and learning the few little touch-ups you need to make it perfect? It's the touch-ups, of course. And the researchers thought, hey, what if we made the AI do that? So the old way forced every single group of layers to learn the entire complex answer from the ground up. The new idea, though, was to let the original information just skip ahead, let it pass through. And then the new layers only had to focus on learning the small correction, or the difference needed to improve the result. This is what's called learning the residual. And by doing that, you take this massive, monumental task and you make it way, way easier to handle. And this is literally what they built. It's like an information highway inside the network. They created these shortcut connections that let the original input signal just zip right past a few layers of heavy processing and then get added back in at the end. This means those layers in the middle don't have to waste all their energy trying to relearn what's already there. They can just focus on figuring out the small adjustment that's needed. And really, that's the whole magic trick right there. It turns out that forcing a bunch of complex digital neurons to perfectly copy something, what's called an identity mapping, is surprisingly difficult for them. But teaching them to just learn a tiny adjustment, or even better, teaching them to learn to do nothing if no change is needed, that is dramatically easier. So did this little shortcut work? Oh, you have no idea. The results weren't just a small improvement, they were absolutely revolutionary. This simple idea didn't just solve the degradation problem, it blew the doors wide open, completely smashing through that depth barrier. I mean, just look at the difference here. It's a night and day. On the left, you've got the old way, the plain networks, where going deeper just made things worse. And on the right, the new residual networks, or resonance for short. With resonance, the golden rule was back in business. Deeper was finally and truly better. More layers meant more accuracy. Problem solved. And just how much deeper could they go? They were able to successfully train a network that was an incredible 152 layers deep. Now, to put that in perspective for you, that was 8 times deeper than the other top models at the time, like VGGNet. And, get this, it was actually less complex to compute. It was a total game changer. And they didn't just keep this in the lab. They took these new ResNet models to the Olympics of AI, the big competitions in 2015, and they just cleaned house. They won everything. First place in image classification, first in detection, first in localization. You name it, they dominated it. And we are talking about huge, huge wins. For example, on one of the toughest datasets out there called COCO object detection, their model got a 28% relative improvement over the previous winner. That's not just a small academic tweak. That is a giant leap forward in an AI's ability to actually see and understand the world around it. Okay, so why are we still talking about a research paper from 2015? Because its impact wasn't just about winning a bunch of trophies that year. It fundamentally rewired how we think about building AI. You see, this whole idea of residual learning, the shortcut connection, it went from being this novel, clever trick to being a standard, essential piece of the puzzle. It's now a fundamental building block that's baked into countless state-of-the-art AI models that we use today, from the ones that analyze images to the massive language models. And the coolest part is, the researchers knew they were onto something huge. Right there in the paper, they basically predicted that this idea was bigger than just their project. They said it was a generic principle, and that it would probably work for all sorts of other problems, even outside of computer vision. And you know what? They were 100% right. It's just this incredible reminder that one of the biggest breakthroughs in AI didn't come from more computing power or more brute force. It came from an elegant, simple insight that just made the problem easier to solve. And that really leaves us with this big, exciting question. What's the next elegant shortcut out there, just waiting for someone to find it, that will unlock the next level of AI? Thanks for diving into this with me.